Let's talk about related rates with more complicated shapes than a sphere. A sphere has a radius and a volume. Let's talk about a former student of mine did an internship at NASA, and they were looking at if you've got some kind of Mars probe, and let's say it's got some sort of rocket exhaust, and here comes all the red fiery exhaust, and let's say it's landing on Mars. As it's getting near the soil, it's digging out a crater using that, accidentally kind of, using that rocket exhaust. So you might say the crater it's digging out is kind of cone-shaped, and they were studying how much of a crater it would dig out for every second of time that went past. So this is the world's best drawing of the red soil of Mars and the red rocket exhaust. So let's model that crater as a cone. What do we know about the volume of a cone? It's 1/3 pi r squared h. So it's basically 1/3 the size of a cylinder with the same radius and height. So this has radius and height. It could be a broad, wide cone, or it could be a really skinny, deep cone. And then we've got the volume. In related rates problems, we usually only like to have one variable on this side and one variable on that side. So not always, but especially for shape problems, that makes life easier. So what we often do is assume that the cone has a constant shape, a constant broadness or narrowness, even if the overall size gets bigger or smaller. So let's write that here. Assume that the cone has a constant shape. But not size. You could say, suppose that the cone has the same angle at the center all the time, but we don't want to get into the trig of angles there. So let's say that the radius is some constant times the height. And this constant would depend on the properties of the soil and maybe the rocket exhaust and the shape of the rocket exhaust and stuff. So that's where a bunch of science comes in. So we'll say science determines this. Based on the sand characteristics. Is it really spherical sand that slides easily, or is it really jagged sand that kind of interlocks? All kinds of stuff. I'm just going to pull a number out of thin air here. Suppose this is 2.9. That would give us a radius that's about 3 times wider than the height, so a fairly wide cone. So then what can we say? We can say volume equals 1/3 pi r squared h, but we know that radius equals some constant times the height, so we could say 1/3 pi, and instead of radius, say like 2.9h squared times h. So I'm just re-expressing this so I have only the cone height on the side of the equation. And then we could say, okay, the h squared and the h gives me an h cubed. So you'd say 2.9 squared h cubed. So this would be especially nice if we knew the current height and dh dt. Because then I wouldn't have to think about the radius at all. But what if we actually only knew something about the current radius and the current rate of change of the radius? So if we knew the current r and dr dt, or we're interested in dr dt, so if we knew or wanted those, then we would rewrite radius equals constant times height to be height equals radius over constant. So then we'd say v equals 1/3 pi r squared, and then instead of h, we'd say r over constant, which we could then write as 1/3 pi r cubed over that constant 2.9. And then we'd have everything in terms of r. So let's go try something like this. And by try, I mean it's on the homework. This kind of substitution also happens in chapter 4.3, where we're optimizing volumes and stuff. And then next we'll try a trigonometry kind of problem.